we're now ready to return to the problem that we started the week with, which was adapted from that list and iterator exercise way back in week 4. So we had this function, for example, pair up, which takes as its input 2 lists, and we know already that iterating over 2 lists in parallel is a bit labor intensive, and it returns one big list whose elements are pairs. And so each pair is produced by pairing up the corresponding elements of the 2 input lists. So the first element of the list of pairs would be 6 and 10, which are the first elements of L1 and L2. The second element of the list of pairs is 116, 106, and so on. We then wrote a bunch of similar functions, like a function that takes 2 lists, this list sum element-wise, and it creates one new list of just ints, that is their sum. So 16, 222, and 298. We did this with their difference and the maximum element. And I illustrated that we didn't seem to have any techniques that could help us. But in the meantime, we learned all about these functional techniques up to and including lambda expressions. I'll run the code as we have it, which is basically the same code we had before. And we can see there are a list of pairs. So 610, 116, 106, 187, 111. There's the sum, there's the difference, and then there's the maximum between the two. So the maximum element in each column. So 10, 116, and then 187. I eventually also want to write this function dot product just to show off how powerful the technique I'm about to use is. So our goal is to take what we had already, which were these heavily duplicated functions. So we kept having to write the same machinery for the loops on the outside, even though the only real difference between the functions was what was happening inside the loops. So there was the maximum, here's the list difference, here is the list sum. And then up here is my pair up function. I make the pair, I add it to the end of my result vector. What I've written to start us off is this function called zip. So I call it zip because in other languages, for example, and I guess maybe the only language I really am thinking of here is Python. In the Python language, the zip operation is used to take 2 lists and pair them up just like our pair up function is doing here. So I actually like the word zip because it sort of reminds me of a zipper. I'm taking 2 lists and I'm sort of using a zipper to combine them into one big list. This zip function, unlike the one in the Python language, it is a little bit different. It isn't actually making a list of pairs. You might have observed in the earlier video, we could have found a way of calling the pair up function in things like list sum element wise to make a big list of pairs and then iterating over the pairs. The problem with that is it has to make a brand new list. It takes the 2 input lists, makes another list, and if our input lists are big, our new list is also really big, and the new list is only ever used to help boil it down into individual sums. That could be a bit of a problem because we could end up running out of memory if we have really massive lists. I want to make sure that I don't need any more memory than necessary. I don't make too many copies of lists. So my zip function takes a function to call on each pair of elements. So each pair would be, the pair of elements in each column. So 6 and 10, 116, 106, 187, and 111. And then the zip function contains all of the machinery to do that. It compares the sizes, throws an exception if they are of unequal sizes. Then it iterates over both lists in lockstep. And it calls the pair function on each pair of elements. That's all it does. The function returns void. And the function that you give it, that you call on each pair of elements, also returns void. But we know from the last few videos with lambda expressions and capturing, we might now be able to rewrite all of the other functions in this file using this zip function to get around all this machinery that we seem to be duplicating otherwise. So let's do that. Here is the pair up function. So I'm going to make my result vector, which is a vector of pairs, a list of pairs. I'm not working with vectors. That would be so much easier. And I'll just leave the other logic in there as I work on my lambda. So I'm going to write a function called pair function, and it's going to be a lambda expression that can work as the pair function argument to my zip function up above. It's a function that's going to take an element of list 1 and an element of list 2. Okay, so I'll call it int element 1, int element 2. There we go. And what do I do at each step? Well, I guess what I'm doing inside the loop, when I actually have both of the elements I'm working with, I guess I just do this. I'm just going to copy this logic directly. And I know there's a one-liner that does it, but I'll keep it as a two-liner. So I make a pair out of element 1 and element 2 using the make pair function. There it is. And then I just push that into the back of my result vector. I should observe, though, that, of course, my result vector is being used inside of my lambda expression. That means I need to make sure I capture it. Because pushback is going to modify the result vector, and that's my intention, I will capture it by reference. And then I just call the zip function. I give it the function to call on each pair of elements, and I give it my first list, and I give it my second list. And before we go any further, let's see whether that worked. I then remove all of this logic here, all of that loop, and I just return the result. Because by the time the zip function is done, my result vector will have all of the pairs I expect. Let's just try running it as it is. And then I'm going to get rid of my diagram because we already know what to expect. And sure enough, there are my three pairs, 610, 116, 106, and 187, 111, just like I had before. I have been able to reduce my pair up function to creating the result vector, which is a little bit different in pair up than the other functions, a lambda expression to do the actual work, and then a call to zip. So much fewer lines of code, but many of the lines I end up with are pretty perfunctory. I don't need to worry about iterators or anything else. Okay, let's see if we can keep going with this. I'm going to copy the logic. I know that I'm going to need similar logic in the sum function as well. So here's the only part of the sum function that's different, where I add the elements together and then add them to the result vector. So I'll make a note to adapt that. Okay, in the sum function, my result vector is of type int, because it's not making a vector of pairs, it's making a vector of individual things. And what I push back into my vector at each step as I iterate over the pairs is element 1 plus element 2. And that's it. That's all I have to do. I get to avoid all that redundancy, all those iterators, all of the loop and the incrementation of the iterators, all of that is no longer my problem. The zip function takes care of it. Okay, we'll push through. Let's do the list difference. And we should know already this should be an easy one because I just changed an addition to a subtraction. There it is. Might as well keep going. Let's compute the maximum. All right, so we'll create our result vector. It'll also be a vector of int. And here I want to do something like if element 1 is less than element 2, or I'll do greater than. If element 1 is greater than element 2, then I want to push element 1 because it's the larger, so I want to push the maximum of the two, push back element 1. And otherwise, I want to push back element 2. There we go. So we'll try that out. We're not yet done the example because there's one function left that wasn't in our earlier example. But if we stare at it, that is the correct set of sums, that is the correct set of differences, and those are the maximums that I was expecting. And I have been able finally to remove the redundancy. There's some machinery left over, but none of that redundancy involving iterators. Okay, one more thing. So the dot product function. Now this wasn't in my original example. I want to do this because I want to show off that I actually, in the zip function, have created something a lot more general than I need. The zip function is for any situation where you'd like to work with pairs of elements. One element from your first list, one element for your second one. You don't necessarily have to be making up your own vector to benefit from that. I could, for example, compute the dot product of the two lists. So the dot product of, well, I should make sure I make that clear. If I have two linear algebraically, these are vectors. If I have two sequences, we'll say x, y, z, and a, b, c, the dot product would be so the dot product, we'll just write that as dot, is x times a plus y times b plus z times c. So I take each pair, xa, yb, zc, I multiply the pair together and then add it into this sum. That's what a dot product is. And there's a great video, I don't know if it's great. There's a video somewhere in the 111 playlist about dot products that you could also go take a look at. Maybe it's great, maybe it's not. I don't know. Send me an email if it is. So what I'm doing here is working with pairs of elements. I'm just going through the elements of first list and second list, pairing them up, multiplying them together, and then adding them into this sum, which I've decided to call dot. So I'll write a lambda expression. We'll call it pair function, just like before. I'm going to capture by reference my variable dot so that I can modify it. I take element 1 from the first list, and I take element 2 from the second list. And then what I do at each step is I just add to my dot product element 1 times element 2. And that's it. Well, I guess not quite. I guess I have to call the zip function. And I give it first list, and I give it second list. So you keep seeing me on the verge of making that mistake I observed earlier, which is where you get so excited about the lambda expression you don't actually use it for anything. And I call it, and I run it, and I think you can verify on your own that that is indeed the dot product that I was looking for. And in the last couple of videos, I've done a lot of these exercises where I write functions with no loops, and it was pretty contrived. Why would I bother with lambda expressions just to avoid one for each loop? But looking at what I ended up with here, this is pretty elegant compared to what I would need otherwise. Compared to the machinery of the zip function, there is a lot of stuff here I really don't want to see. And so because I have lambda expressions, I can choose to avoid writing one for each loop, or I can choose to avoid writing some horrifying terrifying sequence of iterator operations. I have all of these options in front of me now that I have lambda expressions, that I have the ability to throw functions around my program. But it gets better. I can't only do that. I can't just avoid using loops. If I want to, I can write functions that work with other functions. We saw a hint of that in the previous video. We're going to see that again in the next one.